Hello, Assalamualaikum and good morning, everyone. I am Naguib from Department of Physiology, Faculty of Medicine, University Malaya. So I'm a moderator for this morning session for UM at breakfast. And then today we have Dr. Kumar Seluakumaran, who is a medical lecturer, DU54 medical lecturer from Department of Physiology, Faculty of Medicine. And Dr. Kumar has many years of teaching and research experience, and his research is mainly in hearing related and has published many articles on hearing screening. And today he will be presenting on the topic novel frequency selectivity test for hearing screening. So without any further delay, I would like to invite Dr. Kumar to deliver his talk, your talk. Please, over to you, Dr.
Good morning to all of you. Thank you very much, Prof. Najib, and all the other attendees. And thank you also to the Breakfast Health team to organize this talk. I'll be talking about our recent work related to a novel frequency selectivity test, which I think will be very useful for hearing screening. Let's first look at hearing loss. When people hear about hearing loss, especially in a clinical setting, it seems to take a back seat because it may not sound very serious illness. However, in terms of prevalence, this is the second most prevalent health condition globally. In fact, it exceeds conditions like stroke or cancers like bowel cancer. And if you look around, actually 1 in 5 people have some degree of hearing loss. And this is alarming. In terms of disabling hearing loss, if you look at the right graph here, you can see roughly on average about 6% of the population suffers from disabling condition, which affects their day-to-day life. And it also has a very deep effect on the economic situation as the aging population ages and this condition becomes more significant. Now, there are many causes for hearing loss. However, today I'll be talking about two most important causes and they are permanent in nature. So clinicians like to divide the causes according to the origin of the problem. So it can be conductive, mixed, or sensory neural. So I'll be the two conditions I'll be focusing on is the aging and noise-induced hearing loss, which are part of sensory neurals. When we say sensory neural, it means that the damage occurs either at the sensory organ or the afferent or neural pathway, and these are permanent deficits. First, let's look at how this damage takes place. So we all know that hearing is one of the 5 senses, but they're also one of the most sensitive organs in the body. In terms of like physiology, you will find that a lot of these sensory cells located within the coil structure, which we call as cochlea in the inner ear, are extremely sensitive and not only to mechanical changes of vibration, but also to blood flow and hypoxia, as they are very much involved in conversion of very high energy source of stimuli, the sound waves, into electrical impulses before they send to the brain. So the two causes that I mentioned just now, the aging and the noise-induced hearing loss, they both tend to damage these very sensitive sensory cells. The damage is quite, the process of this damage is quite complicated, but to summarize, just I put up a picture here. So for example, it's just not mechanical vibration that damages it. Together with it, there's oxidative stress, inflammation. In fact, the hair cells can undergo apoptosis, and therefore, and finally, when they deteriorate, the nerve undergo deterioration. Let's first understand what happens in the cochlea when the sound comes in. So sound is composed of many different frequencies, the sound that we hear, like speech, music, and so on. The cochlea acts like a frequency analyzer. So it sorts out all the different frequencies, the higher frequency at the basal region. So if you take the coil structure and you straighten it out, the basal part codes for the higher frequency, whether the apical part codes for the lower frequency. So you can imagine this as like a keyboard, right, of different notes. So the high pitch notes at the basal area and the low pitch notes at the apical area. Both the noise exposure and aging effects, which is the most common causes of the sensory neural hearing loss, affects the basal part first. So here the damage of the sensory cells take place and causing high frequency hearing loss. When we say hearing loss or hearing function, clinically we try to measure it using what we call as hearing threshold. This is the softest sound a person can hear, and we present sounds at different frequency, and then we plot a graph. And if you look at the graph here, so this is hearing threshold. So the larger the hearing threshold, the higher the hearing threshold, the worse the hearing loss is. And this is the frequency of the sound. So 8 here will represent the basal end of the cochlea, whereas the apical end is here. So you'll find that as we age, because we are born with a fixed number of sensory cells and these cells do not regenerate, there's a gradual loss as we get older. It starts about 20, some early 20s, and then you will see a pronounced shift once you enter into 50s. And the aging effect is actually worse for male compared to females. And one of the reasons could be because the males traditionally are exposed to more noise, especially in the occupational side. And we know that noise exposure can also accelerate these aging effects. So someone with excessive noise exposure can have years which are when they're 30-year-old, and they can have years which are 60 or 70-year-old years. Now, let me summarize. What is the problem now? The issue is hearing loss tend to be very silent. This type, especially the gradual, cumulative exposure of noise, compounded by aging effects, usually unnoticed in the initial stages. We are not aware of the changes that are taking place. And as it gets worse, when we reach an older age, then we will see the functional deficits kicking in. Another issue is it's permanent. Since it do not regenerate, there's no treatment available. Therefore, once the sensory hearing loss or the sensory cells are damaged, it's not possible to reverse your hearing. So one most important thing in this situation is you have to pick things early. Therefore, early screening is crucial to detect the initial changes and then allow the patients to take precautionary steps so that the hearing loss or hearing can be preserved. So what is available now? The most standardized, or rather most globally accepted hearing test is audiometry. It's a behavioral test where you ask patients to hear different types of frequencies of sound. They press buttons when they hear it, and we track the softest level of sound you can hear. This test, we can then plot these thresholds, the hearing thresholds, using a graph called audiogram. So this is an example of audiogram. If you have someone with either aging or noise-induced effects, both which occur at the basal area of the cochlea, affecting the high frequency. So you'll find that the hearing thresholds are much larger. So the worse the hearing threshold, the higher the hearing threshold, the worse is hearing loss. However, audiometry has many limitations. One, it's expensive. You have expensive equipment. You have to buy a sound boost because you have to keep these subjects in a very quiet environment because you are tracking the quiet thresholds, which means the threshold which is the softest level of these sounds without any background noise. So definitely it's not going to be portable unless you have you have to rent a lorry which carries the booth around. It requires strict calibration, again, because the quiet thresholds is you have to produce exact sound level, and this is then because you're tracking that sound level. And finally, it's also not very sensitive to early stage of hearing loss. Most of it is the clinically, we say that the hearing loss is diagnosed when it's more than 20 dB shift in hearing. Whereas a lot of the early hearing losses and early damage to the hair cells or sensory cells happen even before that. So over the years, what we have been doing in the department is actually to come up with a alternative hearing test, which is portable, low cost, self-administered, which means the patients can actually test it on themselves without requiring an audiologist. It's functionally meaningful, which means you can predict what is wrong with them in a real life scenario, and it would something that would be ideal for mass screening, especially at an early age, suppose in schools and so on. And as a result, we have successfully came up with something that I think would be useful. We call this as a frequency selectivity or FS hearing screening test. So let me just briefly explain to you the basis of frequency selectivity. Basically, FS is the cochlear's frequency resolving power. As I told you, our sounds that enters in the ear, like speech sounds, are composed of many frequencies. So the cochlea actually sorts these frequencies out, analyzes them, and at different areas of the cochlea, the base is high frequency, apex is low frequency, and the membrane, which is called basilar membrane, vibrates according to the different frequencies and produces a peak at these different locations. So if you have many frequencies, the peaks are produced at different levels, and the ability of this cochlea to produce very sharply tuned peak is what we call as frequency selectivity. So the sharper the tuning of the cochlea, you'll be able to differentiate these frequencies better and send it to the brain so you can perceive the sound. So actually this cochlear frequency selectivity is a fundamental basis for hearing. But unfortunately, it has not been tested regularly in clinical setting. We always rely on the sensitivity of the cochlea to the sound. So let me just explain the difference between hearing sensitivity and frequency selectivity. So what we call as hearing threshold that we test in audiogram or pure tone audiometry is the lowest sound intensity a person can hear. While frequency selectivity or frequency resolution here refers to the ability to distinguish these different frequencies or changes in sound. As an analogy, I've given a picture, a visual representation here. Suppose you can see a picture. So your visual sensitivity is the ability to see the image. However, the resolution that you get is what determines the clarity of the image. So in this case, you can have good sensitivity but poor resolution. Similarly, in hearing, you also have poor selectivity, although you'll be able to hear the sound. So there's some physiological basis of frequency selectivity is important for us to understand before we go into the testing itself. So as I told you, the sensory cells in the cochlea, they're very sensitive. There are two types of these sensory cells, inner hair cell and 3 rows of outer hair cells. The noise exposure and aging typically affect the outer hair cells. And we know this over the years of experiments, animal experiments and human experiments. And when these outer hair cells are affected, they in turn affect the tuning of the cochlea, which I mentioned earlier, where the basilar membrane, it has to be sharply tuned to have good frequency resolution. So this is affected. And in turn, it affects the tuning of the neural component. So when the nerves are poorly tuned, this then affects how you tune the cortex to hear different frequency of sound. That affects the interpretation of sound. So both in noise damage and aging ears, you particularly have the outer hair cell damage, which is most very sensitive. So we know that it affects hearing sensitivity because outer hair cell amplifies the basal membrane vibration. This is what we know over the years. This is what audiogram picks up. However, what we are trying to introduce here with the newer test is that not only it affects the sensitivity, it broadens the cochlear tuning. This is an example of representation, what we call as auditory filters. So this broadens up and it leads to poorer frequency selectivity. So the psychoacoustical basis is a bit technical, but I'll try to summarize this for those who want to know more. We can discuss after the talk. But so instead of presenting just pure tones, which are just single frequencies like audiometry, we present these stimuli together with background noise, which acts as a masker. So this masker will mask the signal and increase the threshold for the signal uh, for the subjects. So there are two conditions here. The first condition, we present a masker without any notch. The second, in the second condition, we take out some energy of the noise around the signal to make them hear better. So on the right side, the graph illustrates the change of the mask signal at two conditions. We call this as Tn and TNN. So you'll see a very high steep slope for normal hearing subjects. However, because of the broader tuning, this is the representation of the tuning, you will have a substantial amount of masking still left despite the introduction of the notch, and therefore you have a shallower slope for those with broadened cochlear tuning in sensory neural hearing loss. So with the slope, a smaller slope, the difference between Tn and TNN is smaller, and we use this measure called TFS to represent that. So TFS is much smaller in those with sensory neural hearing loss, especially those with the noise exposure and aging ears compared to normal hearing. The next part of the talk, I will introduce our recent results, and I'll summarize this into four based on what we have found. One, we can use this hearing test and run it through low-cost portable devices. And because we are using mask signals, thresholds are higher, unlike audiometry we use in quiet. They do not require sound booths. We can do this without it, and it doesn't require very rigid calibration either. Second, we have seen over a few years now testing in various type of patients that they have very high sensitivity and specificity to detect this particular type of sensory neural hearing loss subjects. In fact, it's more than 90%, and it's superior to what even WHO offers. And we can use self-administered method, which means it do not require audiologists. We can run on devices which allows the subject to do self-testing. And finally, most importantly, I think it correlates with functional deficits where you can predict speech and noise difficulties, especially in conditions like hidden hearing loss, which I'll touch later. So now I'll give you some details of the publications that we have come up with. So when I say low cost, portable computer based, so we've developed a software which can run on a laptop, and testing can be done with just consumer earphones. We use insert earphones and we overlying ear muff, which then that's why we do not actually need a sound booth. Okay? And secondly, we also have shown that the changes in the this TFS measure, which we're talking about in this test, is very frequency specific. For example, on the right side, this is a graph which shows changes in the quiet threshold. So TQ here represents quiet threshold, which we track in, for example, in a test like audiometry. On the y-axis is your TFS measure from the test. So blue dots represent those data from normal hearing subjects, which you expect because your change in your quiet threshold is less than 20, which means they're within normal. So the category more than 20 would be hearing loss. So here you have subjects which are having a good hearing threshold or hearing sensitivity, at the same time having good frequency selectivity. On the other hand, the red dots represent data from those with sensory neural hearing loss. In fact, these are mild frequency sensory neural hearing loss. You will find that they're distributed across, the reason being that the data that comes from this quadrant are the data which are more than 20 dB hearing loss. This is actually from the frequencies which are high frequency 4 and 8. Whereas here, they are coming from the lower frequencies, which they still have normal hearing. So what it tells us is that just like audiometry is very frequency specific, and this is one of the greatest strength of the test. So I talked about WHO test. This is available. Those who want to do test their hearing, you can go to download this app for free. The WHO offers this in their app store, and both for Android and iOS. So how this test work is you have three digits, and you press, you hear these three digits and you press the number. It's correct, it moves on to the next set, and like that it tracks how well you hear and sound. So we have actually tested our frequency selectivity test against this digit triplet test in Malay, and so uh, I'm happy to say that these tests actually perform much better. And as I told you, because the speech sounds are not frequency specific, they do not differentiate the high frequency hearing loss alone. And whereas this test, you can see a much better correlation with the amount of hearing loss or changes in hearing sensitivity, especially at 4 kilohertz compared to 1, which means it's more sensitive at higher frequency. Next, we also have come up with self-administered testing, or what we call as automated testing. This software allows subjects to press buttons without an interference of an audiologist or a tester. And we have shown good retest reliability, both intra and inter session for this testing. So we have repeated testing of TFS within the same session, and in different sessions, which means different days. And I mentioned about high sensitivity and specificity. So any screening test, you have to do a ROC curve to show the sensitivity and specificity level. So this is a preliminary data that came up, we published last year. So where we compared, first we compared the manual method against the automated or self-administered testing, and then looked at the sensitivity specificity, which exceeded 90% for a mild sensory neural hearing loss. However, we have went on this year. We have tested more subjects, different grades of hearing loss, and it withstood the same level of sensitivity and specificity. Finally, I'm going to show some data on how it correlates with functional problem. One of our FRGS grant is about the testing, FS testing in a group of subjects known as hidden hearing loss. These subjects, they come to the clinic complaining of difficulty in speech, in noise. That means they can't clearly hear speech in noisy environment. But when you do a normal clinical audiogram, they're normal, yeah, within 20 dB hearing. So we have tested using TFS, and we have found that TFS is a good predictor of whatever is happening within their cochlea. And more importantly, what we have shown here in this graph, so both TFS at 8,000 and 4,000 correlates with their speech in noise reception threshold, which is a test that we use to measure their speech in noise ability. So this, again, is very promising because it actually tells us that you can predict your functional problem better than probably your audiogram. And lastly, I just want to give some future directions for this work. So we were looking at further refinement of the testing protocols. We're looking at developing more robust normative data sets across diverse populations. We're interested to work with other centers to establish this data. And we want to further validate the diagnostic efficacy. So far, it's mostly screening basis. So this would be important if you want to take it another step and introduce it in a clinical setting. And then also for those users, probably it's best to have an app-based testing using a mobile. And we have to come up, we actually came up with a prototype. We have one where you can run the test in a mobile setting, but it requires fine-tuning and further refinement. So finally, thank you very much. I would like to take the opportunity to thank Shikin. Shikin was my PhD student and started off with a project. First project we looked at on the FS testing several years ago. Right now, she's actually a lecturer in our department. So she works closely with me with all the projects. Prof. Jayanti helped us in the last 2-3 years to recruit subjects from the audiology clinic. And also thank you to all the audiology staff at the ENT department. And next, we have two collaborators, one from IUM in Kuantan, Prof. Saiful. I think he's also available for this morning session. And Prof. Nomani from USM. Both are audiologists. And Prof. Saiful has helped me with the speech and noise testing part. Prof. Nomani is currently a part of FRGS grant to look into the electrophysiological changes in the hidden hearing loss and how they correlate with the TFS screening. And a lot of the data that I showed today belongs to, the work was done by my PhD students. So Xinyang Esther is from China. She's in third year and currently writing up a thesis. Farah is another PhD student who's working on the hidden hearing loss. So thank you very much. Before I complete, just on the right side, you can see it is no coincidence that WHO has used eggshell to represent the hearing. Reason being that once you damage this, you're not going to reverse it. So please take care of your hearing health. Thank you very much.
Thank you so much, Dr. Kumar, for an interesting talk this morning. So if you have any questions, you can write on the chat box. One question from Dr. Krishna asking whether this degeneration of sensory cell can be recovered by tissue engineering. What do you think?
Thank you very much for your question, Krishna. Actually, people are working on the regeneration of hair cells. There are various ways. They're even trying out some medication, the growth factors, and so on. But clinically, none has been successful so far.
Okay. Also from Krishna also asking about tinnitus. Is it something to do with degeneration of sensory cells?
Okay, tinnitus has many causes. We can categorize as peripheral and central. So the some tinnitus has an origin in the ear. You're correct to say that. But many times, what you see in the clinic is actually central in origin, which means the neural hypersensitivity or hyperactivity that people hear as sound. You must understand tinnitus is phantom sensation in these cases. So there's actually no sound input to the ear. Rather, the brain interprets a signal that comes from the neural firing as sound. Just like when you close your eyes, you can still see lights, right? These are not real lights, but they are created within your brain.
Any other questions from the audience? I have a questions regarding the sensory neural hearing loss. You said it's mostly due to aging, but nowadays in young people also you can find this. So what are the incidents of young adult or young, teenage that's suffering from sensory neural hearing loss?
Yeah, thank you. So I think about 10 or 15 years ago, when I first started off, we did a study in the school, high schools around and we found the incidence of about 5%, where these students usually listen to MP3 players at that time, iPod MP3 players. Currently, the usage pattern is completely different. They're using handphones more regular, at a higher volume. A lot of them sleep with their earphones in. We don't have current data for Malaysia population, but overall globally, it's expected to be much, much higher now. So I would expect roughly to be closer to 20% of the population. Yeah, which is very alarming and worrying because they're very young, and you can imagine the change, the effect in a long-term effect when they reach adulthood.
So the screening test that you are developing now, are you going to use it in the screening among the school children or there's university students that now having a habits of listening loud music.
Yeah, definitely. That is one of the main reasons why we're developing something that is self-administered and low cost, where they can probably download this as an app and run a test using their consumer earphones.
So any other questions from the audience? So it seems today that we only have one talk for the breakfast at UMHealth. So I think with this, I would like to thank again Dr. Kumar for a very interesting talk this morning. So we have a better understanding on this importance of frequency selectivity uh, for hearing screening tests. Okay, with that, I end up this morning session. Thank you so much for everyone for participating.
Yeah.
Thank you.